Okay, so we did the following. We calculated the force on a wire in a magnetic field, and what was that given by? Don't. Okay, never is. Don't have to panic. My coffee will be found. It's over here. Okay, that's good to know. Okay. We can appreciate something. Okay, so this is IL cross B. If I have a wire like this, and if I have a another wire like this, what is the force on those wires? On the force. So let's give these names here. This will be wire 1, this will be wire 2. I want you to find the force at wire 2. So it's on wire 1. So what would that be? Up, down, right, left, in, out.
That wire 2 is wire 1.
Yes.
In.
I'm hearing an in. I heard an it. I don't know what pronouns are.
Well,
It refers to.
well, it depends on where you're at.
It depends on where you're at. I'm just reading what people are saying.
It's not right. Like 7.
It's like 7.
I don't know.
That's cryptic. Okay, that's okay.
You guys not-
Yeah, I know what you meant. Yeah, I know what you meant. But it's,
How do you say that?
you can say it's like 7
Okay, so.
o'clock. Okay. Go to the development. Ow. Okay, what do you have to? You have to do 2 things here first. What are the things you have to do? You first have to find.
Oh,
Okay, why does this wire here? Why does this wire here even experience force?
I was thinking one.
Okay, this wire here experiences the B field from this wire here. So let's give these names. What's the magnetic field from this wire here?
2.
Yes, this is the force that wire 2 is going to exert on wire 1. How does that right hand go? Right hand go.
It's out of the board.
Okay, you grab hold of with your right hand. You grab hold of that wire, putting it on the direction of the current. Okay. Things are like this. So how does magnetic field go on this side? Comes out on this side, in. So we're going to worry about this side here because this is this right here. This is the B field from wire 2. So when we do this, this right here is the B field from wire 2. This wire here experiences that B field. So how does that force go?
Force goes as L cross B
Why did you say L goes up?
because L is the direction of the current.
Exactly. The direction of L, the length of the wire, is in the same direction as the current. So the fact that the current's going this way means that L is going this way.
The current of the wire that's being moved, not the current of the wire that makes it.
The current of the wire that's carrying the current in the external magnet.
Not the one that's making it.
Yeah. So what do? You do the L is going this way, so it's L crossing the B. So this right here is the force that wire 2 exerts on wire 1.
Wait.
That makes sense? You know, are we still in focus here?
No. Actually, sadly, we are.
Yeah, but it's not entirely. Viper, can you see that fine? Will that help you, Viper? I'm hoping it will.
I don't think he's there.
Well, he'll watch the recording.
Oh.
And this will be the check to see if Viper watched the recording. Okay? Viper, did you see this joke? Have you? Have you seen the joke? So, whoa. Okay, so does that part make sense? Now let's ask you a different question. Let's ask, what is the force that wire 1 exerts on wire 2? So find force that 1 exerts on 2. So we'll put this over here. This is I1, this is I2. Not looking at any of these. they were chalk, they'd continue to chalk.
What you should do is make a marker with a chalk outside, some of them inner runs out. You just write with the marker itself.
Yes,
Yes,
we will, okay?
that's what needs to be done.
Okay, proceed. So what is the force that this wire here experiences to this wire here? What's the first step you have to do?
The B field, it's
field.
in,
You have to find the B field from this wire here, which is what?
it goes in.
Grab hold of the wire, putting your thumb in the direction of the current, your fingers wrap in the direction of B. So we get this guy over here. This is the B field. B from wire 1. Now what?
I cross B.
Now you're gonna do this I cross B. So how does the L go for this wire? Goes in the same direction as current. The L goes this way, so it's L. Cross and B, the force is this way. This is the force that wire 1 exerts on wire 2. Why could you have guessed that even without this course? As soon as you knew this guy here, why would you probably have guessed this guy? Give me again, hint, first semester physics.
Currents are opposite.
There's just conservation of
Newton's law. Which one of his laws? The third law, right? That if you have, basically, this is experiencing a force from this wire here. So by Newton's law, Newton's third law, this wire here will exert an equal and opposite force back on the opposing, back on the original source here. What would that equal? Suppose I want you to actually find. I want you to find the magnitude here. What would that equal? Start brilliant. See, a lot of people don't even realize that. You guys are, you're not even done with the course and you realize it's stuff. Brilliant. So we have to look at the magnitude of this I, L, cross B. And this is going to be the I for which wire? We want wire 2 here like this. This will be like 2. And this is going to be the B produced from wire from the first wire here. So this will give us I2 L cross B1. Tell me what my friend here equals. Sine magnitude of I2. Magnitude of L2. B1. Sine 90. Sine 90 is 1. What is the magnitude of B1? Magnetic field for a long straight wire is. Yeah. This is our. Is mu naught I over 2 pi r. Where is the r in this picture? Yeah, this r is going to be the distance between these wires. Which I goes in there?
The one that exerts the field.
And the one creating the magnetic field, which is this one here. This is the I1. So this guy here is going to be B1. So you end up with basically this I1, I2. It's going to be not here. Open an L here like this. That's what that force would be.
L is just.
Whatever the
portion
is. Does that make sense? Good. So how far can I go this way before I go off?
If you put your hand right there, go further. You can still go further. You have like inches, like 10 inches. Right there. Yeah, that's it.
So this picture is edges. It changed. For some on that computer, I can go up to the. Wow, I don't know why. Shows you the inferior aspect of technology. Just regular stuff. We're all the way to the end.
You just use your eyes instead of camera.
Okay, any questions with that? Okay, what I want to do is you're going to come back and do more applications. I want to, since your homework is due when? Wednesday. There's one more type of problem out there that you don't know how to do yet. I want to show you how to do it. And then we're done basically with Cantor's law. And then you can do everything on that. Okay. So we talk about current varying when you have a current density that actually varies.
Just number 8.
The last problem, whatever the last problem. Okay, so let's ask how can you count for wires? A non-constant. Turns out you can't. You just have to omit those problems and go on to something else. Yeah. No, just have to. I don't know how to do it. So let's take an example here. So let's say here is a wire like this. Radius here R. And let's have let's say J is give me a J.
2R.
2R. Let's have fun with J.
2R cube over 5.
Let's say 2e to the minus 3R.
Wow, that's really good.
Okay.
Wow.
Crazy. Okay. What I want you to do is find be everywhere. So how many B's will you be finding? What are they? B, yeah, the inside, which would be B less than
R.
big R, and then R greater than big R. So we're gonna have these two cases here. So, can't wait to find out. So, how would you know about finding the B? As soon as you'd be asked this, what physics would you do? We have two ways of finding B. What are they? The Ilsenberg and Ampere's law. Okay. Tell me the indication of when you know which one to use. When would you use the Ilsenberg?
With the wire solenoid.
No, the Ilsenberg.
That means the circular wire.
Yeah, the circular sections of wire. It doesn't have to be a whole section. Some sort of circular section and straight line sections. Okay. Again, you can use it for any case, but good luck doing that. And then meaning using it easily. So if you see like a straight line section, curved section, and a circular section. Straight line sections you think fields are bar. Okay. When do you use Ampere's law? Infinite solenoid, toroid. Okay, now I told you something here. With the Ampere law problems, what are there's only really one type of problem you can really get with these. What are they?
What's that variation?
You can only get really one type of those problems. It's only the infinite solenoid. Okay. For the subreason, there's only one way to be the solenoid. Once you've done the solenoid, you've done the solenoid. There's nothing else to do with the solenoid. Once you've done the toroid, you've done the toroid. There's nothing left to do with the toroid. So the only variation I can get my cats can do, I think they will, crazy cats. Okay, will be some variation on something like this. Yeah. Because that's the only thing.
We'll have a speed.
That's not one of the things. Okay, that's not one of the problems. Any variation on these, the problems become pathological. I mean, pathological. Okay, so proceed. What do we do? So we look at this and we think we have to do what? Ampere's law. Okay, so this is an obvious Ampere's law. Okay. So what do you do with Ampere's law? You draw your Amperian loop. Okay. So we're going to come out here. We're going to come out here some distance r. We draw our Amperian loop. And to make life a little bit easier, I'm going to draw a top view of this. So if you look at a top. So how would the J be going here? Right, we're saying J is going up like this. So what would we be doing this page here? Yeah, the J is coming out here like this. J's, you know, I can put a little circle like that. So that's enough. So now what's the next step? What is Ampere's law? Line integral, so this guy here, B VL equals U naught I enclosed. So, tell me more. How does B have to go for this one here? If the current's coming out, how would that B go? So you're pointing your thumb in the direction of the current goes, your fingers would wrap like this. So you get these concentric magnetic fields like this. Right, so we pick our favorite spot here, let's say here. This spot here, the tangent to the magnetic field is like that. Okay. What? Tell me about my friend VL.
Same.
It's a tiny little piece, and I'm going to take it along there, and it's always tangent to that little loop. So the little VL. This is my little VL.
VL always follows the current.
No, the current would be coming out like that. Okay. You're thinking about when you have the when you do the VL throttle like this. That's a wire. If you want to find the magnetic field from here, you draw your little the current, let's say the current like that, then that can see the tiny little section of the wire. But again, it's still going to be a little tiny section of that gap. And just in this case here, it's just going to be along that. That makes sense? Okay, so we get what? We get magnitude B, magnitude DL, cosine of 0. What can we do with this and why? Yeah, the magnitude of B by symmetry has to be the same anywhere along here. So I can pull that outside of the loop. Cosine of 1. And so we take a load DL. So the magnitude of DL is a tiny little length here. And again, what does it mean to integrate? It's a summation process. So if I take this little length plus this little length plus this little length, if I add all these little lengths together, you end up with the circumference of the circle, which is 2 pi r. Now, the next part is going to be the hard part. It's not that. You have to keep it. Now, what's the definition of J? J is current density, which is badly named because that's current per unit. So for J, current per unit area. But don't write this part down. This is wrong. Okay, why can't we just say the following? So why can't we say? Okay. J, which is this 2e to the minus 3r, is going to equal our current I enclosed over the area pi r squared. Okay. Why is that fundamentally wrong? We can do that before.
It's not constant.
This is not constant. Okay, this story is along here. Our I enclosed is this guy here. This is I enclosed. This is I enclosed. Oh, we can't do that because you can see that the J here, the J is going to vary as from the one. So what do we have to do? Put in the details. Yeah, you treat this as a collection of rings. So what do? You come out here. I'm going to come out here some distance. I'll call this R prime. If I'm here at R prime, what is the current density here at R prime?
2e
to the minus 3 R prime. Where in this picture do you have the exact same value of J?
Over that.
Any circle along here like this. Okay. Now we need to write the area for that. So what are we going to give that circle? Tiny width called what? I say that the little width here. So I'm going to shade this in. This is the Bob Rossi part of the happy little ring. That's current going all through. Hi in the morning. You current coming through? Yes, you are. Okay, so that's what we have for this. Now I'm going to write the J for this. Yes, you got be the current. So we can say J here. Okay, how much current is coming through that little ring? Di. Some small fraction of it. Over what area is it coming through? You know the area of this ring. Yeah, so again, this is a little strip. If we want to get rid of that strip, remember, we take it, cut it, lay it flat, make it a rectangle. So the length is 2 pi r prime, the thickness is r prime. So we need just 2 pi r prime. This right here, this is the area. That the eye is going through. And my friend J is over here, so this is 2e to the minus 3r prime di equals 2 pi r prime d r prime. Okay. So my current di, I take all this over to the other side. So this is going to be 4 pi r prime e to the minus 3r prime d r prime. So if I want I enclosed, what do I have to do? Yeah, I have to sum up all the contributions from basically all the rings here. I can view this region. Here's a whole bunch of nested rings. Right? This ring, this ring, this ring, this ring. I'm going to add up all the little rings like this. Okay. So where do my rings go from? Which are? If there had been a hole of any radius A, where would you be integrating from? Now, we are going to pull out the 4 by the property of pulling out 4 by. And how do we do that? This is the most important integration technique you use in physics.
You can use
Think what you have to
We are
do
not going
first.
to do that.
Think what you have
Use
to
of
do
one.
first.
well, couldn't you say u equal minus 3 over you had 3 over and then pull out the u? No sense that
you can't.
would be a pipe.
This is a what? Integration by parts. We're going to integrate this part, then we're going to integrate this part, and then we'll apply. Integration by parts. Okay. Use integration by parts.
So minus 1/3. Well, because you have to for that one.
Okay. So how do we do integration by parts?
You set u equal to something.
I agree. U equals
R
R prime.
Yes,
And then-
since you couldn't use.
and then v
Why not?
equals.
Because
Well,
it
because if you
can't.
set u, b percent would leave us u to the minus 2u.
All you're doing is basically.
Are you fine?
Wait, actually, can you use?
No.
Wait, but does that leave you with u, b to u?
Yeah,
And then you could.
that's why I think.
If you do a U sub, you're just going to get a U here, e minus U du. You haven't done anything. You've just changed it. If this were our square, square.
Yeah.
It's not. So you're gonna U equal R prime, then dV equals e to the minus 3R prime, dr prime. Du equals
1.
du equals dr prime. V equals
Negative 1/3.
minus 1/3 e to the minus 3R prime. Now, if we do this. What do? We do this times this. Oh. So this times this is going to be what? This would be R prime 3, e to the minus 3R prime. What do we have to do with that term? Evaluated it at the limits. Then we have to subtract and what? The integral from 0 to R of this times this. That's what we have to do. this picture has to go notice if we're in the science, if we're in, let's see, Olin. That's okay. They have infinite blackboard space, and nested blackboards and everything for their business equations. Heaven forbid you can't make a graph and supply versus. Okay, so what happens? And again, I'm not. Okay, makes me happy that they have all the blackboard space they will ever need in their environment. Okay, so what does this equal then? This term gives me, so this would be minus 4/3 over 3 r e to the minus 3r. Does the lower limit contribute? No, if I had a hole in a radius a, would that contribute?
Yeah.
That would contribute. 'Cause you haven't made that. Okay. Minus make a plus. So this 4/3 here. I mean 4/5 there. What does that equal? So this is going to give us a minus 4π/9. E to the minus 3 or prime. That makes sense? So what does this equal? Not go if I go down wrong. Yes. This is minus 4π/9. How many would I get? E to the minus 3r. That's from the lower limit. If you're to rearrange that, what you wind up with is I enclosed equals. I'm going to start off with this positive term, then get minus and a minus, I think, and plus I'm going to start off with that term. So that'll be 4π/9. Okay, then I'm going to have this term here. Minus 4π/9. E to the minus 3r, then my buddy over here. Minus 4π/3. E to the minus 3r. That looks a little on the ugly side, so you can write this as 4π/9. Yeah, I'm just going to practice. Minus, I'll take out the 4π/3 in this one. And this is going to be 1/3. Okay. Blah blah minus. Well, can I do that in my head? 8. So this would be 8π, right? What, right?
Wait,
not,
you
16, right?
12, right?
16. Boom, boom, boom.
Yep.
Bam.
Working factors.
Math is good.
Can we factor out 4π?
Yeah, you could, but I like to live in I would agree with that. All I did was going to come not make it.
Let's look at 4π/3 have the r.
Damn it. Fine. Caleb wants a correct answer. Okay, so he wants a correct expression. Okay, but watch what we're doing, because we're using actually the secure technology, not called marker. But we're not done yet. Okay. This guy has an R, so we can fix this by going with an R.
That's
So now we're ready like that. Thank you. When you see me do something stupid, call me out. Don't let me do either way. Okay, so I'll pull out still 9. This is going to be 1 minus 3r. Minus 3r. Everyone sure I got this R? Or do I drop that? Okay. And again, on the next test, you'll only have like some. I would not have you do any integration by parts number, right? I would just give you polynomials. I won't give you, I don't mind doing it here for homework or in class. And a test I will do.
Hyperbolic sign.
My section, I like hyperbolic functions. That makes sense? Question? No, we're not. That makes sense? Okay. Now let's finish it up. So this is my Muna here. I'll pull out this 4 pi 9 here. Right through by 2 pi r and Shazam, I have an answer. I really need that answer. Actually, that's over here. Okay, so this gives me that b is I'll kill the pi, I'll kill the 2 here. This will give me 2 minus naught 1 minus 1 minus r. And that's what you'd have guessed. Again, if that was intrinsically obvious, you're going to be a physics major, but you want to. Okay. And men in black will show up at your house, with sunglasses and stuff like this in the piece of paper. Questions for that? I'll finish it up. Tell me why the next region is easy. Plug it in. What's our next region?
It's not going from 0 to R. Lowercase r. It's just
Tell me why, if you're careful here, there's very little work. No.
I enclosed just goes to big R.
Yeah, all we do here, we have the exact same expression here. Now we integrate this from 0 to big R here. We can't keep the same form here. Why? Because if we do this, what are we saying?
It extends out.
Yeah, we're saying that that charge extends and it's not, it's confined to that way. In this case here. Exactly, from this side. So this guy goes to our same b2 pi r. My friend I encloses this guy here.
Why is it lowercase r on the left?
Because if you look at the big picture here. Here's your R.
Oh, yeah.
So thank you. You're currently. So this part here. And this guy here is just going to be this little r equals big R. So this is 4 pi over 9 minus 4 pi over 9 big R minus 3 big R. Boom. B. Pull out the 4 pi, the same thing. This will sort of be 2 ninths. Now there's going to be a little r here. This problem is fair game with the exception of I'm not giving you an integral that you have to do integration. I give you one and you will certainly see one. I give you something more like, J is like this, something we can do. I won't give you something, 3r cubed hyperbolic sine of r to the 4 16.
Is it even? I'm not sure that you actually.
Oh, you can, you have to do it from there.
Hyperbolic sign.
Hyperbolic sine. The nice thing about hyperbolic functions, you get to talk like, oh, we are all Babylon 5, one of the greatest science fiction shows of all time. You have to watch it though. The first season is hard because it's setting up actually a really profound story. There's Kosh. Stay close to the Morlock. Stay away from the channels. Okay. So that's how Kosh is. We're all Kosh. He is the closed circle. It all makes sense. You find out why he's a closed circle. Questions?
Aren't you missing a R in the first B?
Am I missing this guy here?
Yeah.
No? It's right there. Okay, I dropped that arrow, thank you. Make sense? Okay, let's do another thing that we're gonna be. So that's really all you can do. The main ones with Ampere's law is kind of like that variation there where you have a varying J and then you just treat it as a collection of, you treat your wire as a collection of the ring you find it correct. That's as hard as it gets for those. If you can do those, then you're fine with all the Ampere laws. Make sense? And everyone wants to. Good. Sure. Okay, let's talk about another application. I'm going to ask what happens if you place a current loop, current carrying loop in an external magnetic field. So let me explain what this means here. So let's say I have a loop like this. So here's a good loop. So here's a current. I'm going to put it in a magnetic field like this. So it's the question is what's going to happen. I'm going to give you the answer, then I'm going to prove it to you. Again, remember I told you we're going to learn 3 chemistry devices. What are they? We already did 2 of them. What were they? Oh, NMR we haven't done yet. Mass spectrometer. Gas chromatograph. Okay. I said though, NMR is going to be one of them. We need this result for actually the NMR. The NMR uses a couple things. This is actually going to be one of them. I'll explain where this is comes in actually very important. For any of you doing any type of material science and stuff like this, this idea here is actually really important. Okay, so the answer is going to be the B fuel exerts a torque on the current given by mu cross B. Now this mu here, and what is that mu? That's our magnetic moment. It's often called the dipole magnetic moment as well. Okay. And what did we say the magnitude of this guy is?
IA.
That's the current going through the loop times the A is the
Area enclosed in the loop.
yeah, the area of the loop. Okay.
And it's normal. So we
Yeah, now there's a right-hand rule for that. And how does the right-hand rule go? So if we actually do yeah,
That's what it says.
is it? Okay, so let's say we have a current loop like this. How do we say how would the magnetic moment go? So you have a current going like this. Yeah, so you take your right hand, what do you do with it?
go in the direction.
You wrap your fingers in the direction of the current goes, so your fingers are going like that. What does your thumb do?
Point in the direction of the magnet.
Points in the direction of the magnetic moment. So the mu here is going to go out like this. So how do you denote that?
Dot.
Yeah. You do dot, circle, and go. Make Make sense? Okay. Just out of curiosity, will electrons and protons have magnetic moments? Okay, let's draw, so you can just see where this is going to go. Let's say here's a proton.
Oh, it's there, like, there.
Okay, how can you view a particle like a proton? It's a spinning ball of charge. Okay, it's not, but it turns out that dumb little picture actually works a lot better than it should. Okay. So let's say this is a spinning ball of charge, and let's say it's spinning this way. If it's spinning this way here, this has angular momentum. How does angular momentum go? What's the right-hand rule for something spinning from 125? You rotate your fingers around the direction of the thing rotates at some points in the direction of the momentum. So this right here, this is the angular momentum. Of the spinning. Okay, when you have an angular momentum of a particle, you no longer call it angular momentum of a particle. What do you call it? Spin. You call it spin. So when people talk about electrons having spin or protons having spin, it really is the angular momentum. And so this is actually going to be our mass. Okay, but if this is also, positive charge going like this, you can imagine that the charge is making little circles like this, little currents like this. So what else would this thing have? It would have a magnetic moment mu. Okay, it would also have a B2. Okay, but there would be a magnetic moment going like this. I mean, the current going like this. And so how would that magnetic moment go? In the same direction. So this right here, this is also going to be mu. Okay. So if you put this in a magnetic field, what would that magnetic field do to that moment?
But how would a point spin? Like in the case of an E electron?
It's not a point.
Well, since-
Actually, it does appear to be a point, although it may not be much of a string.
But
But
like,
that's not.
well, since if you have a zero dimension.
Yeah, they have an intrinsic spin. If you're born an electron, you have a spin. That is assigned to the particle. Take an electron, turn it over. The quantum number is going to be s equals a half. Turn it over, it says s equals a half electron, God. Okay, meaning it's been put there by God, you can't change it. That's
Well, it's just kind of weird, since if you have something that is a point,
it's an intrinsic property of the particle.
then what? Then, oh,
It's not
It's-
actually.
It has, you can't view it, as I said, this is a cartoon picture. No, it's an intrinsic property. It has spin. Actually, it has to have spin because of electron. The person who actually showed this, his name is Paul Dirac. And he's the one who did relatives of quantum mechanics. When you do relatives of quantum mechanics, the electron has to have actually spin. Not just that, it turns out it also picks up. Okay, now if you had an electron like this, let's say here's an electron, I could view this as spinning like this. So how the angular momentum for that particle would be here. So this would be the angular momentum, that's for the electron. Now, if this is a negative charge going like this, then you would go this way, but what do you think the magnetic moment's going to do? The magnetic moment for the electron is going to go like that. So what's going to happen here when we do NMR, we're going to take these particles, we're going to put it in a magnetic field, and that magnetic field is going to put a torque on that, and that's going to cause these spins to fly. And then something else happens. Okay. That's where that's coming in. And we're going to be flipping spins. Okay. Or electron spins. Okay. So what I want to do is I want to prove this result. I'm going to give you a little bit of quantum mechanics later on when we get to this point, just so you know there's some things I'm not going to be able to prove to you. And we're just going to have to state it as, take it as gospel. There's a reason you can prove it, but not at this level. So let's do a proof of that. So we're going to take a square loop. So let's take a square loop like this. We're going to have to do a couple pictures of this. And so I'm going to take a square loop like this. That. Okay, I'll call this L. I'll call this W. I'll take a beat. So if we did a side view of this, you're gonna have this guy here. This is gonna be my wire. The current's gonna be doom, boom, 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 going like this. In other words, so here's my loop. Okay. It's gonna be like this. Current's going doom, boom, boom. Here's my loop. Okay. So let's figure this out. Hey, what am I gonna do to that little tiny wire loop? Split it into 4 pieces. So call this side 1, side 2, side 3, side 4. So if you ever have to have like a magnetic image done of yourself, if you yourself have that MR done, when you're in the machine, just start screaming as loud as you can and say, "Don't flood my protons! Don't flood my protons!" No one will think it's anything. Just scream as loud as you can. It'll help the doctors. They're flipping my protons. Stop it. Yeah, nothing better to do. It's always good to scream when you're in the machine like that. Okay, so it's like you should scream, right? As I told you the first semester, right? When you're in an airplane, you get ready to look at the lamp. What did they tell you? What did they say when they're going to land? We'll be landing momentarily. Why should you just start screaming and panicking? Because what's landing? What is landing momentarily? That's landing momentarily. And you should start screaming. Okay, this is what they should say instead. We'll be landing soon. Just F. Okay. So where was section 1 here? Yeah. We have this part here, the wires coming here, and how would that current go for section 1? This is here. And that's section 1 right there. Current's going out like this, right? It's going out like this. It's going out like this. Okay, where is section 2?
That's the line.
It's going down like this. This is section 2. This is section 2 here. Where is section 3? Right, current's going out, down. Here's going into the board. So here's going into the board. This is section 3. Okay, where's section 4?
Behind this.
And then it's coming back out this way here like that. So this is going to do double duty. So we have that. Hey, what's the force on side 1? What do we know about this? The force is equal to IL cross B. So what is going to be the force on this guy right over here? Right here. Do the right hand rule for this. Okay, how does L go for the side 1? Comes out. Okay. So do I cross B, I, right? Because this is the direction of L. Right, L's in the direction. Cross into B, that goes up. What about on side 2? So this guy here, this would be the force of this. So L cross into B, so what do I have to do with my hand? I have to flip it. So it's going to be L cross into B like that. That's going to be out. It's going to be something like this. Tell me about my friend 3. Current's going in like that, so let's L cross into B. This is this guy here. This is that 3. So this guy here on this side is like that. Oh, sorry, F1. Tell me about my side 4. Okay. L cross into B. That guy's like this. So where's our torque coming from?
It spins.
Yeah, this guy. So here's your wire. If I pull up here, if I pull it on there, what is this going to do? That's going to rotate that. That makes sense? That's where the torque is coming from. So what we'll do, we'll start off with this picture tomorrow. We'll calculate what torque is. Where do you think this is going to rotate about?
center and.
about the center right here. So we're gonna calculate the train about that, and Shazam, we're looking at this guy here. Okay, have a great day, see you in lab today.
Well, but if that's going to.
Lab today, we're gonna do a VR.
Oh, no, I see. Oh, so.